Radio access network accounts for 73% of telecom operators' energy consumption. Energy-efficient RANs reduce carbon footprints and lower OPEX, aiding telecom sustainability. Artificial intelligence machine learning, AI/ML, has proven effective in boosting RAN energy efficiency. This demo showcases AI/ML in optimizing energy efficiency within an O-RAN environment. The O-RAN Alliance introduces non-real-time RAN intelligent controller and RAPs, empowering integration of advanced AI/ML technologies to drive innovative energy-saving strategies. Within AI/ML, both supervised learning and reinforcement learning, RL, are applicable to energy-saving use cases. RL agent learns sequential decisions to maximize energy efficiency through frequent interactions with the network environment. RL algorithm operates as follows. An RL agent collects network data and takes energy-saving actions to the physical network. The agent learns to optimize energy savings via repeated interactions, which is costly, slow, and risky. To mitigate these issues, we introduce digital twin (DT) technology. The RL agent learns energy-saving strategies, a model, within a synchronized DT network of the physical network. The trained model is then deployed to the physical network for ongoing fine-tuning and validation. In this demo, we showcase the combined benefits of reinforcement learning, digital twin, and O-RAN REAK technologies in enhancing energy efficiency within O-RAN networks. We developed a set of RAPs on a non-real-time REAK platform. The key performance measurements, KPMs, are reported to REAK via O1 interface. The KPM RAP then shares these KPM data with the DT translator and evaluator RAPs to synchronize the physical and DT networks. The traffic prediction RAP predicts network traffic loads and providing inputs to both the NES network energy saving RAP and DTNES RAP. The DTNES RAP interacts with the DT network to pre-train a decision-making model. This pre-trained model is then deployed to the NES RAP as an initial knowledge for interacting with the physical network. The NES RAP continuously fine-tunes and validates the model during interactions to the physical network. The DT translator RAP converts the physical network data into parameters for the DT network, ensuring accurate representation. The DT evaluator RAP compares the KPM data from the two networks to assess their alignment. This process may be executed iteratively to ensure consistent and reliable synchronization. We consider a scenario where a coverage cell and a capacity-boosted cell are collocated. In this scenario, we demonstrate how the NES RAP deactivates the capacity cell during low traffic periods in the coverage cell for energy savings. In this scenario, we demonstrate how the NES RAP activates the capacity cell during high traffic periods in the coverage cell to maintain QoS requirements for target UEs. In this scenario, we show how NES RAP decreases the transmission power of the capacity cell to optimize energy savings when the target UEs are positioned near the capacity cell center. The test was conducted on the QCT's O-RAN-based end-to-end 5G solution. The DT network was constructed by VIAVI TerraVM AI RSG, RAN Scenario Generator. Singapore University of Technology and Design, SUTD, and QCT integrated OSC non-real-time REAK and the system under test, and developed a set of RAPs in this demo. The actual hardware of the 5G system under test, along with the testing equipment, was hosted at the test lab in Singapore. The VIAVI TerraVM AI RSG used for building DT network was deployed at SUTD. The construction of the DT network involves two key phases. We first deploy a DT network using VIAVI TerraVM AI RSG. Our RApps facilitate synchronization from the physical network to the DT network. In this experiment, we demonstrate how the NES RApp sends commands to deactivate the capacity cell during low traffic periods. During the movement of the target UE, the DT RApp continuously monitors the performance of both the physical network and the DT network. The NES RApp sends a command to the capacity cell for a graceful shutdown before the target UE is handed over to the coverage cell for energy saving. We can observe that both the physical network and the DT network are synchronized to perform the same action. In the left figure, we show the convergence behavior of our RL algorithm in both the physical and DT networks. Experimental results demonstrated that the trained RL model achieves approximately 20% energy savings for the capacity cell compared to the original always-on network within a working day. With pre-trained models on the virtual network, 90% of training time and interactions can be reduced compared to directly training the model on the physical network.